damped case. Okay, so then the problem is this. So the question is this. Given this problem, what choice of gamma maximizes the amplitude of the particular solution? So this is the sort of big boy version of resonance. Now, there is a easy way and a hard way to do this problem. The hard way to do this problem is to use real notation. Right? If I was to use real notation, I would guess that the solution has the form A cosine gamma t plus B sine gamma t, right? But I know if I use complex notation, I can get through this in a much nicer way. So what we do is we look for a complex particular solution. Yp equals to A e to the I gamma t. See, because I know if I can figure out what A has to be here, then I'll be able to figure out then from looking at the real and imaginary parts of this. Excuse me. I'm going to guess this. I want this to solve the corresponding sort of the complexification of this problem, which is this m d squared y, it's a word, dt squared plus, you guys snickering over me saying complexification, so here plus ky equals to f naught e to the I gamma t. Okay? This, yeah.
In our original equation, what is the amplitude? So with x value of y, what are we looking
at? Right. Good question. Well, the solution is going to be sines and cosines, so it'll literally be amplitude of the sine or cosine solution. So it will make sense once we get into the details of the problem, but I know at the moment that might not even make sense. So anyway, the point is here, if I solve this complex version of the problem, right, if I replace this is a little different than what we've done before. What I'm proposing is we replace the force with a corresponding complex force that takes the given force as a real component, right? Then, if I solve this complex problem, it follows that by basically complex superposition, it follows that the real component of the particular solution we find is a particular solution to the corresponding real problem with f naught cosine. So if yp is this, what's yp prime? I gamma a e to the I gamma t, right? Or, as I might prefer, this is I gamma yp. What's yp prime prime? I gamma squared a e to the I gamma t, or if you like, minus gamma squared yp. So plug these in to the given differential equation. What do we get? Not the given differential equation, excuse me. Plug these into the complexified differential equation, this guy. Plug these into star. What's that give us? It gives us m minus m gamma squared yp, right? Plus IB gamma, IB gamma yp plus kyp equals to f naught e to the I gamma t. Now, of course, I can rearrange this a little bit. Right. Yeah, fine. So I get myself minus m gamma squared plus IB gamma plus k all of this times what? Times a e to the I gamma t equals f naught e to the I gamma t. You see what's going to cancel here, right? What are we trying to find? The undetermined coefficient, by the way, is what? There's just one of them right there. Okay. This naive guess works because there's no overlap here, right? How do I know there's no overlap? Because we have assumed we're in the underdamped case. Assuming we're in the underdamped case forces the homogeneous solution to include an exponential. And exponentials do not overlap with pure cosines. Right? No matter what the gamma is, the homogeneous solution doesn't match up. So we can just use naive variation of parameters and propose our solution as basically the same form as the forcing function and its derivatives. Check it out. A is equal to f naught over minus m gamma squared plus ib gamma plus k. Man, I feel like I've got a sign error here, but I don't know where it's coming from. All right. Now that's not quite what I want, is it? Because we would like to put this in Cartesian form, right? How do you put that in Cartesian form? Multiply by the complex conjugate of the denominator over the complex conjugate of the denominator. These are just numbers. Don't be scared of them. K minus m gamma squared minus ib gamma divided by k minus m gamma squared minus ib gamma. Right? That should do the trick. That gives us f naught times k minus m gamma squared minus ib gamma, all divided by k minus m gamma squared quantity squared plus b squared gamma squared. Finally, my solution, my real solution. So in engineering book, guys, a lot of times what's done, so let me kind of embrace the jargon. So we'll put tildes on the complexified problem to remind ourselves, hey, this isn't the real problem, this is the complexified problem. And so the solution we just found, all right. So what I need is yp is going to be the real part, all right, of the complexified one we just found. So I need like the real part of that. Let me just write it out this way. It's the real part of a e to the I gamma t. In other words, it's the real part of a times the cosine of gamma t plus I times the sine of gamma t. That a is complex, right? This is the a. So you could rewrite this as like a1 plus ia2, right? And so multiplying that out, let me just get to the point here. That gives us, a1 cosine gamma t minus a2 sine gamma t. Because when you multiply a1 plus, when you multiply a1 plus ia2, the real part is going to be like a1 times cosine minus a2 times sine. Everything else has an I in it left over. And so that is going to give me, you're like a headache. No. Let's not go there. F naught k minus m gamma squared. I'm more worried about a coughing fit. Times the cosine of gamma t minus that minus, so I get plus, stupid thing, come on, plus b gamma sine gamma t is divided by k minus m gamma squared plus b squared gamma squared. Let's see here. Now, if you guys look at equation 6, all right, on page 221 of your textbook, you'll see that what they have there is exactly what I have, but they've derived it in a radically different way. What they did was they put y as a sum of sines and cosines and just differentiated. I wanted to again showcase for you the method of thinking complex. It's useful, it's important, especially for if you're electrical. We like to do this sort of thing to solve circuits. We replace a sine function with its imaginary exponential complexification. Solve that problem easier way with these so-called phasors, and then you can extract the sinusoidal solutions from that. Okay, so that's the particular solution. What's its amplitude? Now that we got this, what's the amplitude? Right. I guess the larger question is, can you add sines and cosines? For example, let me look at a slightly less scary problem. What if you had 2 cosine x plus 3 sine x? You know that that's equal to a times the sine of x plus some phase angle. How do you find a? Let me work backwards. So this, right, is like a sine x cosine phi plus a sine phi cosine x, right? So if sine and cosine are linearly independent, they are, we can equate coefficients. So this 2, right, has to be this thing. And this 3 has to be that thing, right? So we have 2 things to work with. We've got 2 is equal to a sine phi, and we've got 3 is equal to a cosine phi. Now, I personally don't really care about the phase angle at the moment. I'm just interested in the amplitude. How do you find the amplitude? I mean, how do you eliminate sine and cosine? May I introduce you to a old friend? Right? So this says the sine of phi is 2 over a. This says the cosine of phi is 3 over a. I think it's clear that a is non-zero, so we're not in danger here. And so this says that 2 over a quantity squared plus 3 over a quantity squared is equal to 1, aka 2 squared plus 3 squared equals to a squared. Aha! A is equal to the square root of 2 squared plus 3 squared. The reason for this is pretty simple. Sine and cosine are actually perpendicular vectors in infinite dimensional space. So there's a Pythagorean identity. The length of a vector in this infinite dimensional space is the square root of the sums of the squares, the lengths of the components of the vectors. The lengths of the components of the vectors here are exactly the coefficients of sine and cosine. And that's why this is happening. But pragmatically speaking, if you're faced with the problem of finding the amplitude of a sum of sines and cosines, provided the sines and cosines have the same argument, it's important that we have gamma t here, and we have gamma t there. If that were not the case, we'd be in trouble. But since that is the case, we finally find our formula for the amplitude using a very similar excuse me. So the amplitude is going to be the square root of the sums of the squares of the coefficients here, right? So we get, downstairs we've got that k minus m gamma squared, right? Plus b squared gamma squared, and upstairs we have the square root of what? K minus m gamma squared squared plus what? Oh, b gamma squared, right? Aha! So the amplitude is really just f naught. There's an f naught in both of those, right? This f naught is, I'm sorry, there's supposed to be an f naught in both of these, isn't there, right? Typo, I forgot my f naught there. Sorry about that. Anyway, long story short, the amplitude is f naught over the square root of k minus m gamma squared plus b squared gamma squared. Now, again, this, well, not again, but for the first time, this is the amplitude as a function of gamma. So next time we'll pick up here, and I'll show you that there could be a choice of gamma which makes that amplitude largest. What are we going to do? Do what? Yeah, take the derivative, put it equal to 0. Right, back to calculus 1 again. It makes me happy that you say that. Sometimes I tell a class of 40 that, and they just kind of stare at me blankly and go, what? So anyway. So we'll pick up back there Thursday, and hopefully Thursday we'll get out a little bit early since I went a little bit late today. Thanks, guys.